We're going to talk about AR and AI on the phone. One of the interesting things is that the first place that people really see AI and AR is going to be on their phone. And so I called it ARCore at mass because it is really, because we all have a supercomputer in our pocket, it's really going to be the first place that we're going to see augmented reality. Now, I wanted to talk a little bit about the difference between AR and VR. If you think about AR, you're actually still in your environment. You can look around and you can see what's around you. When you're in VR, it pretty much completely takes over your environment. What you're hearing and what you're seeing and what you're playing with is completely virtual. And for me, the best is the mix of the two. So I would think that the new upcoming Apple Glass or the new Google Glass is probably the best of both worlds. Not AR's great and VR's great, but I think mixed reality is really where it's at. So I just want to give a really quick definition. AR is anytime you have a virtual image on top of the real world. And so we've all seen lots of examples of AR, and we're going to get deep into how AR works and some examples of AR, but we've all seen it. Anyone who used the Snapchat feature or Apple's ability to put an image on top of your face on the phone, we've all experienced AR. And the reason that AR is where it is, it was coined back in 1992. That was the first time people started talking about AR. And for a long time, since 1992, people have been doing research in it, but it hasn't really gone anywhere until like 2008. In 2008, AR really exploded. So we ask ourselves, well, what happened in 2008? What happened is everyone started walking around with a supercomputer in their pocket. Right? What do you need to be able to do AR? It has to have a display, tracking, input devices, and a supercomputer. But that's exactly what I have on my cell phone, right? I have a very powerful CPU, a camera, accelerometer, GPS, and solid-state compass. So after 2007, we started seeing a lot of AR apps being built on the phone, and people really started seeing AR in the mainstream. Now, the first examples of AR when I first started working on it, it was kind of like very cumbersome to work with. There was like a Connect app that allowed you to put clothing over yourself so you could see what it looked like before you bought it, or other applications that let you use the camera and they put markers inside the camera so you could see, you could get more information about the information that you were getting through the camera, right? And this was a kind of a interesting application where you, in your rear view mirror, you got to see all of the lanes of the street of the road that you're driving on and what lanes are going to be going the fastest. And what's interesting about this is that if everyone is looking at the same augmented reality, they're all going to move to the lane that's the fastest, making it the slowest. So I just thought that was a very interesting use of augmented reality. And also, people would put images on top of their camera, but this is an image that makes no sense because at the time, the AR systems did not have a way to find a plane, and so for them to put an image down and know where the road is, this was not possible at the time. But I guess someone was trying to do some PR and made that image. The kind of stuff that we were seeing back then was something like this Mattel. And what Mattel built was Rock'em Sock'em robots, but with just using augmented reality. And the beautiful thing about this is you don't have to build an entire factory to be able to build this Rock'em Sock'em robot. You just have the person go to their printer and print out this piece of paper. And then through the Qualcomm AR experience, they're able to figure out what the camera is looking at. And then over the web or over Wi-Fi, they're able to figure out what the two robots are doing.
What is this?
And then they're able to show you what the Rock'em Sock'em robots looks like through each of the phones. Now, we can do this today without the printed page, and we're going to get into the technology that shows how this works. But this was an early concept, and it really made architects really excited about the fact that they can now go look at the buildings they're going to build by just printing out a piece of paper. And Mattel doesn't have to use a ton of plastic that can't be recycled to make their toys. They can just have someone download an app and print out a piece of paper. So the early examples of augmented reality really needed a marker to be able to know where to put the models. And here you can see when we get into trouble, because wherever that marker is, that's where the model is going to be placed. So if you were to pick this guy up and hold it in midair, then the marker would just the model would just be running in midair, which is not a very good experience. But for the time, it was quite remarkable. So this is the kind of legacy equipment technology we were working with. It was called like mixlar.org, and you had to use the camera, the compass, GPS, accelerometer data, a lot of things going on here. It was very complex. And then Qualcomm came out with another augmented reality framework to allow you to build something like Rock'em Sock'em robots. Again, it was very cumbersome to work with, and I think the licensing was quite expensive. We've come a long ways from there. So now, if we look at what we're able to do, this is called ARIse, and it's a really cool example of one of the AR apps that runs on the iPhone. And it uses perspective to be able to allow the guy to walk around the world. So as you're holding the phone and you're exploring this world, depending on how the perspective that you use to look at the walkway, it'll either make a bridge or it'll leave a gap. So you have to walk around and get to the right perspective so that the little guy can walk across the various planks. And this is really interesting in that you can get really close and get really good idea of the detail, and also explore the world from a lot of different angles. So there's a lot of different really cool AR examples I could get into, but I thought I'd get deeper into how the technology works. There's 3 new things that were added to the latest version of ARCore. So not only can you build the AR apps that I just kind of showed, but now you can do augmented faces with the latest version of ARCore, and they don't use depth perception to find the points on the face. So they find 468 points on your 3-dimensional face. They build this mesh, and they do it with artificial intelligence, right? So they're not using anything more than a normal camera to be able to do augmented faces, which means that almost any type of Android phone out there can do augmented faces. Where with the iPhone right now, they're using the LiDAR camera to a large extent to be able to make this mesh face. But if you think about it, if you have millions of pictures of people's faces from all the different degrees, you can teach a neural net what the mesh would look like on any face. So again, AI is used here to be able to make the mesh. And they also have augmented images, so that when you hold your phone up to an image, they can put an AR model on top of that image. And as you move the image around, the model will track with it. So those are 2 things that were recently added to ARCore. And the third one is they really got the lighting correct. Before, ARCore would not be able to do lighting as well as it can now, where when you put in a light source, when you detect a light source inside of your AR, it does an amazing job making it look like it really belongs in the scene. So to understand how AR works with ARCore, we're going to start from the beginning. A long time ago, there was a phone called Tango, and Tango had a depth sensor in it, and motion tracking. Now, this was really unusual at the time to have 3 cameras on one phone. Today, it's a standard where the Pixel 5 has 3 cameras and infrared. The iPhone actually has 3 cameras and LiDAR, and the Samsung has multiple cameras, and its time of flight depth sensor is again infrared. But at the time when Tango first came out, it was the only phone that had multiple cameras and sensors built into it. And its main job was to be able to do indoor mapping, right? So you would walk around with the Tango phone, and it would use its motion tracking, depth sensing, and its high megapixel camera, and it was able to do 3D mapping of the physical space you're in. So it would do X, Y, Z, pitch, yaw, roll, and then a 7th dimension would be time. Now, the Tango phones were absolutely amazing, and Lenovo and Asus were both going to make these Tango phones, and they were relatively inexpensive, $599 and $499. But what's amazing about these Tango phones is neither one could run ARCore. So when you bought these phones, yeah, it could do 3D mapping. It could find planes and vertical surfaces for you to put your AR components down on, but it couldn't run ARCore. And so this starts getting into the meat of, well, what is ARCore? Now, for a long time, the iPhones could do augmented reality. And that's because Apple has been thinking about this for a long time, and they had this chip in there, and the chip is an IMU. It's an internal measurement unit. And it's made, the reason that you need this chip is because you want to be able to do simultaneous localization and mapping, which is called SLAM. Anyone who's looked at any pictures from a self-driving car and the LiDAR point clouded builds, that's SLAM. You're doing simultaneous localization and mapping, and that's what the LiDAR allows you to do. Now, we need to be able to build a point cloud, because the point cloud is going to allow us to give us enough information about our environment so that we can put our AR, our augmented reality models into our physical space. Now, what's really important about the need of an internal measurement unit is that the internal measurement unit allows you to build this point cloud. And the way it does that is it does something called dead reckoning. And with dead reckoning, what you do is you're able to look at the frames that are coming in from the video, and you're able to figure out a stereo, a 3-dimensional image from those pixels that are coming in from the video. And the way that works is we need to know exactly the position of the phone as those frames are coming in. Now, this will not work with low light because we don't have enough features between the different frames to be able to figure out which pixels go where. We won't be able to do it without shadows, right? So we have to have light, we have to have shadows, and you have to move the camera. If you try to do this on a tripod, you could run ARCore all day long on a tripod. It will never build a single point in the cloud, right? Because it needs to see the differences in the frames to know which pixels are moving faster and which pixels are moving slower. And that's why when you actually are given a ARCore app to run on your phone, one of the first things they show you is move your phone around, right? Because what they want to do is they want to be able to find the different pixels across the different frames to be able to make the point cloud. Now, once they have figured out the point cloud, what they do is they look for triangles that line up in the same horizontal plane. And once they get those triangles all lined up, then they can say, okay, this is a surface. Once they have a surface, they start looking at the screen. And when you tap on the screen, they make a projection from the screen onto that surface. And that's how they know where to put the anchor of the augmented image that you want to put into the scene, right? So your augmented model is going to be placed on the anchor after the point cloud figures out where the surface is. So why did Google, 1 month after they made Tango, completely throw it away, start making phones with the AMU chip in them, and release ARCore? And it's really because of Apple, right? So in May 19th, 2007, I went to Google I/O, and they were talking about Tango, but there was no such thing as ARCore. July 5th in 2017, ARKit was released. And then August 29th, 2017, ARCore was released. Because Google really couldn't have iPhone being able to do augmented reality on their phone, and Tango wasn't going to get them there. So they basically scrapped Tango, started making phones with the AMU, and started building ARCore, started building phones with ARCore. Now the iPhones had this IMU in there for a long time, so a lot of their older phones could run ARKit, but only the new phones from Google could run ARCore. But now all of our phones can run ARCore. So ARCore has some really nice major points. One, it does motion tracking. By looking at the phone and using the IMU, it knows the position and the orientation of the phone as you walk around. So it's able to keep virtual objects in the real space as you walk around it. Also, it has environmental understanding, so it knows planes, vertical and horizontal planes, and it can do light estimations. And those three major points are really important when you're trying to do augmented reality on a phone. Now, I just put these links up here so that if you want to get deeper into doing ARCore, you have some resources, but I'm going to kind of walk you through on how you would build this. With ARCore version 1, it took a lot of code to be able to build an AR environment. Now with AR version 2, it's 90 lines of code or less. But if I show you how AR version 1 works, then you're going to get a good idea of how version 2 works. It'll even be easier. So there's a package for session, a package for frame, a package for plane, and a package for anchor. This is everything that I was trying to explain when we were looking at how it works, right? Because you're going to start a session. It's going to start reading in frames. It's going to build a point cloud. It's going to find a plane. And then when you touch the phone, it's going to project into the point cloud and hit a plane, and then it knows where to put the model. And that's exactly what this code is doing, right? So if we look at the major packages, session, frame, plane, anchor, and we look at the major objects, it's anchor, frame, hit result, plane, point cloud, pose, session, right? And before, when I gave this talk, I would actually walk through the lines of code. So if you go to this GitHub repository, lines 122 to 148, we're building the scene. 170 to 279, we're looking for the planes. 327 to 433, we're figuring out where the person's touching on the screen, and then we're going to figure out where to put the anchor. And then 352 to 355, we go and we get the model, and we go and we put the model into the scene, right? Now, with ARCore version 2, it's much easier to do that, and they added some features that are amazing. Number one, the AR experiences can be shared, because when you put an anchor down, it actually goes into the cloud, and we call that a cloud anchor. And what happens there is those cloud anchors are visible to everyone who's in that space. Because if you think about it right now with ARCore version number 1, when I touch the screen and I put down an anchor and then the system puts my model on my anchor, I'm not sharing that with anyone. But with version 2, when I touch the screen and it figures out my GPS location and it figures out what plane I touched, it holds that in the cloud. That means that everyone around me can now see where I put that augmented reality model. Another cool thing is that it can do both vertical planes and horizontal planes. Before, version 1 could only do horizontal planes. And also, the AR experience is much faster. With version 1, you actually had to walk around a pretty good amount of time before you got the point cloud. And then it took like a long time for the point cloud to figure out where the plane was. And then finally, when the plane was generated, you could touch the screen and it would put down the anchor and the anchor would go on top of the model. With ARCore version 2, you basically just have to hold the phone for a second and the planes are generated, and then you touch the screen and you're able to see the model. Now, for AR version 2, it's way easier. It's less than 90 lines of code, and I went ahead and gave you the GitHub repository for you to do that. But basically, all you do is you make a fragment, an Android fragment, which basically sets up the scene, the point cloud, finds all the planes. Super easy. It's one line of code. Then what you do is you go ahead and you load your model. And this model could be made with Unreal Engine. It could be made with Unity. It could be made from a whole bunch of different tools. And I'm going to show you a bunch of tools so you can render your models. And the last thing is we just look for where you tap on the screen so we know where in the scene to place the model. So if you're out there and someone says, hey, we're looking for augmented reality programmers, and you've never done it before, go ahead and say, hey, I'm an expert in this. I can come in and do your augmented reality programming. Because Google took care of everything for you. They give you the scene, and they give you the tag. The company's probably going to give you the model that they want rendered. So, with very few lines of code, you are now a certified augmented reality programmer. Now, when you're working with ARCore, you need to bring in models. So I give you some, because that is the real star of the augmented reality experience, is the model you're going to put down. I give you some links here, so both Unity and Unreal Engine, you can go and learn how to build your own models. One of the interesting things is when you tap on the surface to put your model down, your model is now fixed to that anchor. But what if you want your model to run around on the floor? Now, you can simulate that by having your model move around your anchor. If your model is too large and it goes off the table, then it's just going to go off into the middle of the air. But, if they put it down on the ground and you have your model running around the anchor, it's going to look fine. So here are some tools for you to go get your models. There's something called blocks that you can use a tilt bledge to make models, but also you can go to the Unity store and buy models. Google has some models, and Unreal Engine has a marketplace for you to go get your models. Once you get your models, it's really easy to use ARCore to build an augmented reality experience. So I really encourage everyone to start looking at ARCore, ARKit, and WebXR because they all follow exactly the same mechanism that I just explained, right? They all talk about making a point cloud. They all talk about finding planar surfaces from the cloud. They all talk about a hit that is going to tell them where the anchor is, and then they take the model and they put it onto where the person touched on the screen. And here you can actually go to a class and learn more about ARKit. And I assume at some point Udacity is going to have something on ARCore. But again, Google has made it extremely easy to do AR programming. And so with only 90 lines of code, you can get your AR experience working. So that's the piece I wanted to talk about AR. I have like a half an hour left, and I really want to just jump into how to build a self-driving car, because it's pretty cool how that works. And then at the end, I'll take some questions. So let me go ahead and jump into this guy. All right. Let me see. Stop that one. I am going to grab this tab. Okay. All right. So in a half an hour, I'm going to explain to you how a self-driving car works. I fell in love with this thing called Pixopolis. For years, I've been telling people that the phone is the most technologically advanced thing mankind has ever made. It's got LiDAR, it's got radar, it's got a super processor in it, it's got GPS, accelerometers. It's absolutely amazing. And I kept telling people, you could probably build a self-driving car with just the phone. So I want to be able to take my phone, put it in front of my car, and have my car drive around itself. And I was kind of joking, but Google went and built it. And here what you see is the Pixel phone is completely autonomous, right? It's using its camera to be able to figure out what these signs are saying and make sure it doesn't hit any other cars. So let's talk about how they built this. This was made for Google I/O. It's right now running in Japan at the SoftBank store. Their largest installation is at SoftBank. And basically they're stations, and you can tell the self-driving cars what station you want them to go, and they will read the signs and avoid other cars and go from station to station. So there's a station app that allows you to tell the cars where to go. And then the car app is not only doing all the AI to figure out what the signs are saying and keep itself on the road, but also controls the motors for the car to be able to drive around. So they made two apps. Okay. Now, for us to really understand how self-driving cars work, we have to understand the difference between empirical programming, declarative programming, and AI programming. So empirical programming, you tell the computer exactly what you want it to do line by line by line by line. And that's how most of us program today. Declarative programming is like how Swift UI and Jetpack Compose work. So on Swift UI, you just say you want a menu. And when you run it on the computer, you get a pull-down menu. If you run it on the iPhone, you get a tab bar on the bottom. And if you run it on the watch, you get it on the crown of the watch. So you just kind of tell the system what you want, and the system knows what to do, right? So again, like if you do Swift UI and you say I want a menu, it's pull down on the Mac, it's a tab bar on the iPhone, and it's the crown on the iWatch. So it's one step up from empirical. Now AI programming is very different, and I'm missing two graphs here. But basically what AI is doing is it's saying, I'm not going to give you the rules of how this system works. I'm going to give you the question and the answers, and you're going to figure out the rules on your own. So the robot, the Boston Dynamics robot, that is millions and millions and millions of lines of control system to get it to run. There's no artificial intelligence in this thing at all. It's just billions and billions of lines of control systems. This one, this one was built by Google DeepMind, and they basically showed a computer, a person running, and it learned on its own over time how to run. So there is no control system in the DeepMind architecture. It learned without any instruction how to run. And that's kind of what we need, right? Now, this is one of my favorite examples, right? This is a convolutional neural net. which means that this is a system in which a computer is just analyzing the pixels of this image, right? Now, it has an error function. So the AI system knows when it's doing good and when it's doing bad. And it's just looking at the pixels of this image. It doesn't know anything. It's just looking at the pixels of this image, and it has an error function. It does not know which paddle it is. It doesn't know it's playing a game. It doesn't know how to score, right? It just knows that if a ball gets past it, it's bad. And if it gets a ball past the computer playing on the other side, it's good. So this convolutional neural net starts learning that what it wants to do is keep the ball from going past it. And what it wants to do is get the ball to go past the computer. So this AI system is learning how to beat a computer. So we have a computer program learning to beat another computer program. Now, the green is the convolutional neural net learning, and the orange is the computer program. The computer program will never get better. Over time, it will never get better. But the AI system, over time, got so good that it knew exactly how to hit the ball in the exact angle, in the exact position, so that the computer could never make another point. So over time, the AI system, by just looking at these pixels, figured out how to just completely decimate the computer program that was the orange. And I just thought this is a really great example of, like, if computers get out of hand, we just make a smarter AI system to beat them. Now, the reason that it's so important for us to do AI programming for self-driving cars is because there's way too many rules for us to be able to codify this, right? It's much easier for us to show a car billions and billions of pieces of data and have it learn what the rules are. And that's exactly what we're going to do in the next 15 minutes. We're going to take a computer and we're going to show it tons and tons of data, and it's going to learn how to drive itself. Now, this goes back to our previous talk where you can see we're building a point cloud with the LiDAR that was provided. Now that we know what an AMU is, we can actually build this with one camera and motion. So if we want to use a Pixel phone to do what a self-driving car does, we're really disadvantaged because the self-driving car has radar, visible camera, LiDAR, infrared camera, stereo vision, GPS, internal measurement unit, cam, and audio, right? My phone doesn't have any of this, but we still need to replicate everything that the self-driving car does, which really goes to talk about just how amazing it is that they were able to pull off this feat. Now, pretend that you don't have a phone and you have absolutely no way, you don't have any devices but a browser, and you want to build a self-driving car. There's this guy, his name is Raj. I just kind of stumbled upon this video. But what he's doing in this YouTube video in 38 minutes is he's using nothing but a browser and a simulator to build a self-driving car. And what happens is NVIDIA has a self-driving car simulator that's executable, and you can just download it and run it on your computer. It runs on Linux, Macs, everything. It's just a little simulator. So in the beginning, what happens is you're going to drive around this little simulator, and it's going to gather data. You're going to take that data, and you're going to train a convolutional neural net how to steer it. And then you're going to take the convolutional neural net after you trained it how to steer, and you're going to pipe those instructions back into the simulator. You're going to sit back, and you're going to watch your AI system drive the car, right? So you're going to drive the car 5 laps. You're going to pull that data into your convolutional neural net, and I'm going to explain what a convolutional neural net is in a minute. And then once that thing is trained, it's going to start driving the simulator, and you can see how well it drives. So that he does all that in 38 minutes. I give you the link if you want to. If you don't have a phone, you don't have anything, you can still build a self-driving car. So why is the Udacity self-driving car simulator so important? It was used in Raj's video. I'm going to talk about it now. The people who built Pixopolis also used it. It's because we don't have a Waymo, right? We don't have a Waymo. We need to gather data of what it looks like for a car to drive around and get all the sensor data from the car so that we can use it to teach the artificial intelligence system how to drive, right? Because we're going to, instead of giving it the instructions of how to drive, we're going to give it the data necessary for it to drive. Well, where are we going to get this data? We don't have a Waymo. Well, we're going to get it from the self-driving car. When we drive the self-driving car, it's going to generate images for us, and it's going to give us steering and accelerometer and brake data. And we're going to use all this data, and we're going to train a convolutional neural net to drive a car. So now we have to explain, what is a convolutional neural net? If you want to know what kind of an image is in a picture, use a convolutional neural net. So here we have 3 channels, red, green, and blue. And we want to know, what is this image made out of? And so what we want to do is we want to make convolution layers out of this image so that we can make a prediction. And the way we do that is we're going to make these convolutional layers. So here we have an image of a number 1, and it's a 28 by 28 by 1. So it's red, or it's black or white, and it's 28 by 28. What we need to be able to do is go from a 28 by 28 to an array of 0 to 10, right? So 10 possibilities down here, 0 to 9, right? How do we go from a shape of 28 by 28 to a probability of 0 to 9? Well, the way we do that is we take these pixels and we're going to apply filters to them and make a new layer, convolution layer out of those that is going to be pulling out features of these pixels as we make the layers. So you can see here I'm going to make a convolutional layer by applying a filter to a region of pixels here, a region of pixels here, and I'm going to make that filter is going to find the features as I go down. So if I take a multiplier and I'm going to do a 5 by 5, a region of 5 by 5 with a depth of 1, and I'm going to go to 4 layers. So I go from 1 layer to 4 layers. And then I'm going to take a square of 4 by 4. I'm going to take in those four layers, and I'm going to go to 8 layers. So then I'm going to do that again. I'm going to go a 4 by 4. I'm going to take those 8 in, and I'm going to go to 12. And then I'm going to go I'm going to take those 12. I'm going to have a filter of a 7 by 7. I'm going to take those 12 channels, and I'm going to go flat to 200. And then from the 200, I'm going to go to a 10. So basically what I did is I took an 8 by 8 by 1, and I took it down to 200, and I got 0 through 9 here. Now what happens is when I light up the pixels in this image, I'm going to apply a filter to them, and depending on what my filter does, it's going to pull out features of this image, and it's going to go through all these filters, and it's going to say, this one you put in, it's a 9. I'm going to say, no, that's wrong. How far off were you from the 1? And depending on how far you are, I'm going to change these weights that are in these filters. And by changing the weights of the filters, I'm going to make it so that the 1 is the highest when I see a 1. And I'm going to put in another number here. And when I put in that number, it's going to go through these convolution layers, and it's going to say it's a 5. I say, no, it's not a 5, it's a 1. So then what I do is I change the weights back. This is called back propagation. I'm going to use back propagation depending on how big my error is, I'm going to go use back propagation to reset these weights so that when I put in the number, I get the right number out. And by playing with these weights and over doing this back propagation, I train my neural net so that when these pixels of a 1 light up, the highest probability down here is a 1. So that's how a convolutional neural net learns what an image is. Now we do one other thing. After I make my first convolutional layer, I do this thing called pooling. You could do average pooling, but here we do max pooling, where we look at the pixel magnitude and we just take the biggest one. So here we can see I'm pulling out the features when I go through my convolutional layer, I'm pulling out the features of horizontal lines. But when I do max pooling, I'm 1/4 the size, and I have highlighted those features. And here you can see my convolution layers. They're actually pulling out the features of these handwritten digits and giving me what that digit is. So the first layer could be looking at horizontal lines. The second one could be looking for curves. The third one could be looking for vertical lines. But they're pulling out features of the images as you go through the convolutional layers so that it can tell you what the number is. And then we use max pooling. So one more time, basically if I put in a picture of a cat or a dog, oh, she's getting pretty hot. Do I have anything running? No. Okay. So if I put in a picture of a cat or a dog, my first convolutional layer will start pulling out features. I use max pooling to turn down the complexity of the image, and I do another set of feature analysis in my next, and I keep doing that over and over again. Feature mapping, pooling, feature mapping, pooling, feature mapping, pooling, until I get to a fully connected layer. And then I say, is it a house? Is it a car? Is it a tree? Is it a dog? Is it a cat? And when I show a cat and it says it's a tree, I use back propagation and I change the calculations of my filters, right, the weights of my filters, so that when I'm showing it a tree, the tree is lighting up. If I show it a cat and it's saying it's a dog, those are pretty close, the cat and the dog, very different than a tree. So I'll change my weights less. And I'll start doing this over and over again. What I'll realize is as I get closer to having all of the pictures correct, I'll be playing with my weights less and less and less, and that's called the gradient descent. I'm making a gradient descent down to the minimum amount of error. Because if I have a picture of a tree and I say it's a cat, that's a huge error. If I put in a cat and I say it's a dog, that's a lower amount of error, right? And so if I show a cat and it says it's a cat, that's the least amount of error. So depending on the error, I know how much I'm moving my weights to be able to train my neural net. Now, this is all really important for us because the way that Pixopolis works is we're going to show it a picture and it's going to tell us, should I turn right or should I turn left or whatever. Now, all of this work that Pixopolis did comes from this paper from NVIDIA. This NVIDIA paper is super famous, so I'm going to run through it real quick. What they did is they took a car and they put 3 cameras on it. And then they drove it around like 500 miles, 1,000 miles, and they captured what do the images look like and how are they driving the car. Then they had a whole bunch of data. And they said, okay, now we're going to train our convolutional neural net. But we're not going to train our convolutional neural net to figure out if it's a cat or a dog. We're going to train it to say, if you see this picture, should you turn right or should you turn left? So what they did is they started feeding in the images of the cameras. And they asked the convolutional neural net, should you turn left or right? Now they know what the real answer was, and that was the error, right? And so through back propagation, like I was saying before, if you get I should turn right and you should really turn left, you're going to go back through this whole thing, changing these weights so that the filters change, so that when you put in a road that turns to the right, it's going to say I'm going to turn right. Or if you say I need to go straight, and it says I need to turn right. You're going to go back up this thing, and you're going to change all the weights in these filters so that when you put in a picture that looks like it's going straight, it'll say, I'm going straight. And that's where this error function comes in. This is the gradient descent that we're doing on our solution space. We want this error to go down to 0. So when I show him a picture, these 3 pictures, he's going to say, turn right, turn left. It's going to be exactly what the steering of the human being was saying it should do. Now, what this paper pointed out is once you have this convolutional neural net trained on the steering, you only need the center camera. Well, when the people who were building Pixopolis saw this, they thought to themselves, we can do this, right? Because we only have one camera on our phone, but this paper proves that the center camera is all you need. And so what they did is they went out, this is still the paper, they went out and they built the convolutional neural net, and this is the actual configuration they used. And to prove to themselves the system works, they trained the convolutional neural net. And they asked it, they showed a picture and they said, what do you do here? And he says, I'm going to turn hard right. And they said, oh, you want to turn hard right? No problem. They said they went into their video archives and they generated an image of it turning hard right, and they gave it back to the convolutional neural net so they could say, okay, you're not doing it right. So then they trained it, and now they put in a picture of it turning right. They showed it to the convolutional neural net, and he said, you know what, turn right. They simulated that image of the car turning right, and they could then see it turn right. So they're manipulating real-time video to make sure that the convolutional neural net is working properly. We're going to do the same thing, but we're going to do this in the simulator. They did it with real video. We're going to do it in the simulator. Now, if you look at the output of their convolutional neural layers, you'll see what features they think are important. Because remember I said that as you go through these convolutional layers, you're pulling out the important features of the image. Like here, you're pulling out the important features of the image as you go through the convolutional layer so you can tell what it is. Well, they did that. And the first layer of the convolutional layer, they can see that on a curved road, the major features they're pulling out are curved. When they looked at off the road, they couldn't tell where the road was. So they knew they were learning where the road is. Now, with that knowledge, the people building Pixopolis said, we are going to use the same technology, but we only need the bottom 1/4. And we're going to put it into the convolutional neural net, and instead of it telling us it's a dog or a cat, it's going to say turn right or turn left. So they went to the simulator, and they put in waypoints. And they started using the simulator to capture the 3 images, right? So the center image, right, left, and you can see down here, they're capturing the images. And they know they're steering, right? So they can use this data to train their model the same way NVIDIA did, to say, if you see these images, this is how you should be training. This is how you should be turning. So they had all of this data, and they had to make, when NVIDIA did their data set, they did it in snow, they did it in rain, they did it in a lot of different conditions so that the system could learn in a lot of different conditions. Pixopolis also did the same thing, right? They did a bunch of different environments to run their simulations so they could get a lot of good data. Now, once they had the data, they could start training their neural nets. And again, just like we saw in the NVIDIA convolutional neural net, the first layer, they are also learning what the road looks like. So this is great, because if it's learning what the road looks like, then they can make the turns properly. One of the things they noticed is when they started putting this thing together, it kept driving off the road. And that was because their first series of roads they built was all straight. So it never learned how to turn. And so they made really turny roads to help it get better data. Now, one of the things that they also added was a long short-term memory layer to their neural net. And this is important for natural language processing, because each layer of the neural net does not remember what the previous layer understood. So if you look at this layer does not know anything about this layer, right? This layer has its own weights and filters, and this layer has its own weights and filters, but these two are not communicating. They're connected, but they're not sharing information. They're just passing along information. So they're connected, they're passing along information, but they're not sharing information. That gets into the problem with natural language processing. Because if you look at this, you say Finland is a country where people speak Swedish. In a standard RNN, this is very confusing because you might think that we're talking about Sweden, but we're talking about Finland. So what we want to do is we want to carry state over from one cell to the next. And the way we do this is we use LSTM. And what the LSTM does, not only does it take the connection from the previous set of neurons, but it also brings over state. And you have a gate here that allows how much state you want to pass through, and then you add that to what this neuron is learning. And what this allows is you can say, okay, this Finland, this is very important. I'm going to let this pass through where the is not that important. So the system learns, I'm going to really hold on to this word. And so when I get to the end of the sentence, this is still very relevant to me, right? So now there's some memory in the layers of the training where it's able to keep some things that it learned before. Now, the reason this is important is because when you have a self-driving car, if you're going straight, chances are you're going straight. And when you start going into a turn, you're probably going to stay in that turn for a little while. It's not like you're going right, left, right, left, right, left, right, left, left, straight, left, right, right, right. So if you have a memory that, hey, I'm going straight, I'm probably going to keep going straight. Oh, I started a turn, I should stay in my turn. This really helped the system work really, really well. And so basically, they had the car running, but since there's no GPS on this thing, they had to teach it how to read signs so it knows where it is. And that's where the TensorFlow object detection is excellent. This is the library everyone uses for image classification. So they went into Unreal Engine and they made a whole bunch of signs and they trained their system on these signs. And the ones that they didn't do in Unreal Engine, they just took images and then blocked them out and trained the convolutional neural net on the signs, right? So here the convolutional neural net is running, and you can see it can tell extremely well what signs are in the picture and what those signs mean. So we have two convolutional neural nets running. One is looking at the road, figuring out if she's turned right or left. And the other convolutional neural net is reading signs so it knows where it is. It knows it should stop, go straight, or whatever. Now, we have been training these things in the cloud, right? We're training these things on massive computers to make the model. But once the model is built, it's very small. So we can actually now take that model and move it into TensorFlow Lite. And TensorFlow Lite is actually what runs on the phone. We don't run TensorFlow on the phone because the phone just doesn't have the processing power necessary to do training, but it has the processing power necessary just to run a model. So once we have all the training, like terabytes upon terabytes of data to train the model, we can bring down a very small model. And what we're going to do is we're going to move it into TFLite. And TFLite is a subset of TensorFlow, so you have to look at the compatibility and make sure all of the instructions that you're using in your model are actually available on TensorFlow. You pick your model, you convert it to TensorFlow, you deploy it on the device, and then you optimize the model. Now, the Pixel Neural Core has a TPU in it. And so what's a TPU? We have a CPU that is super good at running general purpose instructions. We have a GPU that's really good with graphics. What a TPU is, it's really, really good with TensorFlow operations. Now, people argue, a GPU is very good at graphics, matrices. A TPU is very good at AI matrices, but they're both matrices. So you get people going that the NVIDIA GPU is just as good as the Pixel's TPU, and you don't really need a TPU because the GPUs do matrix math really well, and the TPU all it does is matrix math. So people argue about if you really need a TPU, and I think the latest version of the Pixel 5 doesn't have the neural core. But the new Apple chips all have their AI system built into it. So when we're done, we have these self-driving cars that are using convolutional neural nets to figure out what the signs are, to avoid each other and drive on the road. So the final thing that was built were several stations where you could control the cars, several destinations that you could tell the cars to go to, and several cars running in collaboration with each other. So not only was the Pixel 4 figuring out what the signs were, what the road was, but it was also controlling the engines of the cars, the motors. So the Pixel phone was really doing everything necessary to make the self-driving car work. And they did an outstanding job. So these are the acknowledgments of the people who put Pixelopoulos together. And if you want to know more about me, I kind of just skipped that part, but you can always go to @biocodes and see where I've talked or what I'm up to and get my bio from that. So with that, I think I would like to turn it over to questions and see if we just get an idea of what people thought, and if there's any questions about how the augmented reality works, or how self-driving cars work, convolutional neural nets, point clouds, anything that's coming into people's minds.